all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. Today's discussion is basically going to be looking at one of the elements of group 3. And this, of course, is going to be a compound of thallium. Now, in this specific case, we're going to look at one of the properties, of course, of thallium's compounds in terms of stability. And that is going to assist us explain some of the analogous configurations that we're going to come across perhaps in various reactions of group 3 elements. Now, in this particular case, I should look at just a summary of some of the oxidation states, and this is going to be giving us some of the characteristics which we are going to witness, especially in terms of course, electrons, the valence electrons, and of course, some of the reactions which are going to be witnessed for these members of the group. Now, in this particular case, spoken about the concept of oxidation states of various elements, and we're not going to go into details about that specific discussion, but I'm going to put a link of those particular discussions in our description box in terms of a playlist. Kindly check and engage us in the comment section so that we can be having a healthy discussion on the same topic. Now, in this particular case, we are going to see that most of the group 3 elements are going to be displaying the oxidation state of positive 3. Among others, of course, we are going to see that some elements as well are going to be having the oxidation state of a positive 1, as we're going to see in some of their compounds. Now, I'm going to give these specific members of aluminium, indium. So this also is going to have a positive 3 and positive 1. And of course, we're going to also see that thallium as well is going to have positive 3 and positive 1 given as such. Now, in terms of course, the most common, or the more common, which is going to be appearing across these specific groups, we're going to see that positive 3 is going to be more common form of oxidation for these particular members of the group of the periodic table. And of course, we're going to see that in some of the compounds, the oxidation states of especially thallium are going to be appearing in a similar way as the group 1 elements which we have discussed. Now, I'm going specifically to look at the thallium, perhaps this is specific kind of oxides, and that is going to be a range of oxides which are going to have this particular oxidation state of positive 1 in terms of this specific element of thallium. Now, we're going to see that, for instance, for thallium oxide, this is going to be a soluble and a strong base in aqueous solution, and it's going to be more stable in this specific case. Now, the stability of this particular oxidation state is going to be associated with what we refer to as the inert Baer effect. Inert Baer effect. Now, we have talked about inert elements which are going to be displaying some kind of a stability and their inability to react in that particular case. Now, from our last discussion on the concept of electronic configuration of various elements, I said that we can give a valency configuration of various elements, but in this case for thallium, I'm going to give an example which is going to assist us understand this specific concept of inert Baer effect. Now, we're going to use the 5D, perhaps I can just do away with this. So we're going to use the 5D orbitals of this specific element of thallium, and then we shall have the 6 S orbitals and the 6p orbital, which is going to be given as such. So this is going to be the 5p orbital of the configuration of thallium, and then we're going to have, of course, in our illustration of the configuration of this specific element, we're going to have this, of course, noble gas members, which is going to be giving us its short form. So we're going to display the last 3, of course, orbitals given as such. So this is going to be the 5d, 2, 3, 4, 5, and this is going to be the 6s and the 6p orbitals given as such. So this is going to be having a full occupation of this specific orbital for the electrons. For the d and the s orbitals, these are going to be fully occupied. So we're going to have these electrons appearing in these specific pairs given as such. And then we shall have the 6p orbital being fully occupied, while as the 6s orbitals being fully occupied and then the 6p orbital being containing one electron given as such. Now the stability of the positive one, of course, oxidation state from this specific case, which the said is going to have or to be due to the inert pair effect, is going to be experienced in such a way that in its reaction, the 6p orbitals are going to be losing this specific one electron, and this is going to retain the 6s orbital in or the 6s subshell, which is going to be, of course, remaining in this particular case. So we can, in a way, have a summary of this specific illustration, or perhaps I'm going just to give this one in terms of the general case we are given for various quantum numbers. So a representation for n s2 orbitals and n minus 1. So I've talked about the n minus 1 representation, so we're going to have that one p6, and then we shall have the n minus 1, and this is going to be the b10, and then we shall have the ns2 given as such. So in this specific case, we're going to see that this ns2 orbital is going to be left after the one electron is lost. And of course, we have decided that this is going to be giving an inert pair effect, which is going to cause a stability of this first oxidation, or the positive one oxidation of this specific element of thallium. Now, in a sense, we are going to see that the lower part of this specific group, there's going to be small bond energies and lattice energies associated, especially with such a kind of large atoms, in terms of perhaps their atoms and ions, which is not going to be large enough to affect these specific, of course, electrons of the ns2, which I've given on the board. So in this particular case, and therefore, I've mentioned that the group 3 elements in terms of oxidation states in summary form are going to be having this positive 3 as a common oxidation state. But for the unique case of thallium, which was our point of discussion for today, we are going to see that the positive one, of course, oxidation state is going to be more stable than the positive 3, or the more stable than the positive 3. And that is due to the inert pair effect, which is going to be experienced due to loss of this electron in the 6p orbital, and then the 6s orbital, which is going to remain with the 2 electrons. These are going to be having this as a kind of a stability which we have talked about. Now, this is due to the small bond energies and, of course, lattice energies associated with such a kind of a large atoms at the lower part of this specific group, which are going to be having less energy that cannot be sufficiently affecting the ionization energy of this specific ns2 orbital, or ns2 electrons being given at this lower part of our illustration. So in this specific case as well, we're going to look at some of the unique cases that we come across in various elements, especially on their oxidation states and some of their physical and chemical properties that we may come across in our various discussion. So I hope that one is clear. Kindly check our description boxes for various links of other videos, and also subscribe and engage us in the comment section so that we can be having a healthy discussion on various topics in science and maths. So that is it for now, guys. Bye. God bless you. Catch us in our next video.